Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at the concept of relations. It'll be a very general discussion. It doesn't really have anything to do with real analysis, and it's a good idea to acquaint oneself with this notion because it is pervasive in mathematics. Okay, so before we go on, we will recap what we did the last time. We discussed what are natural numbers, and well, these are natural numbers. I can't say much about them, as I mentioned in the last video. Whole numbers are just natural numbers equipped with an extra symbol called 0, and again, we can extend all the things that we do on natural numbers to whole numbers like addition, multiplication, the usual ordering, etc. And we discussed a very important principle in mathematics, which is called the well-ordering principle, and that says that every non-empty subset of natural numbers has a smallest element. We saw some examples as to how to apply the well-ordering principle, and then we finally discussed the notion of integers. This is the notation, z with a extra slash. And well, we know what integers are. It's basically all the quote-unquote positive integers and the negative integers, and including 0. So that's that, and now let us go to the material of the lecture. And before that, these are the 3 problems on the well-ordering principle. So it's a good idea to pause the video and solve all of them. And now let us define what is a relation and why do we want to discuss them. So the formal definition is as follows. Let X be any set, could be infinite. A relation on X is a subset R of X cross X. So, well, what is X cross X? X cross X is just the pairs of elements in X. Right, so any subset of this guy is called a relation on X. So it may not be very clear what we are trying to capture. Basically, when you pick 2 elements in X, whenever, suppose you pick x1 and x2 in X, and suppose you are given a relation on X, then you call x1 and x2 related if the corresponding pair is present in R. It will be clear when we see some examples as to what is going on here. So that's a relation, and let's see at least one example. We'll see more in the future slides, but for now, here is one example. So let P be a set of people set of human beings, basically. So not all human beings, just some human beings you have collected in a set. And now here is how you can define a relation on them. So we say that we define R as those pairs in P cross P such that P2 is a child of P1. So this is how we can define a relation. Basically, this relation is that of a parent. So if P1 is a parent of P2, then we just record that data in this via this gadget. And of course, R is a subset of P cross P. So that's basically, this is a good example of what is a relation. In fact, this is a paternal relation in the colloquial sense. Okay. So there are some special kinds of relations that we are interested in. So a relation is called reflexive. Reflexive if, so relation R on X, or even before that, let us also introduce a notation. So if R is a relation of on X, and A comma B is in R for some A and B in X, then we may write A R B. So instead of writing this may also be written. It's just a matter of notation. Okay. So now a relation R on a set X is called reflexive if X R, what am I doing? If X R X for all X in X. This is the notation for all, just a shorthand, for all. Okay, so reflexive, it is faithful to the terminology. It's a good terminology basically. So X, when you have a relation which has the property that every element is related to itself, you call it a reflexive relation. We say that R is irreflexive. We say R is irreflexive if it is the exact opposite of reflexive. So if this never holds, or rather this holds for no X, so we'll see examples. One example of an irreflexive relation is the one defined here. A person cannot be a parent of itself, or himself, herself. Right? You cannot have X comma X or P comma P in this set, because that would mean P is a child of P, but that's absurd. So that's an example of an irreflexive relation. Let me give you an example of a reflexive relation. So this is an example of a reflexive relation. So let R be a relation on N, be a relation on N defined as those pairs of natural numbers such that M divides N. So this is a reflexive relation. clearly, because any integer, any natural number divides itself. So of course this is a reflexive relation. Another important class of relations is symmetric relations. A relation R on X is called symmetric if whenever we have x1 r x2 for some x1 and x2 in X, we have x2 r x1. Right? So that's a symmetric relation. And an antisymmetric relation R on X is called antisymmetric if whenever x1 r x2 for some distinct x1 and x2 in X, then we don't have x2 r x1. So just like irreflexive is the exact opposite of reflexive, antisymmetric is the exact opposite of symmetric. So here you have an antisymmetric relation. This is an example of an antisymmetric relation, because if suppose you have m comma n sitting in this relation such that m is not equal to n, then what that means is that m divides n. So if m is not equal to n and m divides n, then of course n cannot divide m because m is less than n. So this is an antisymmetric relation. Right, and we'll see examples of symmetric relation just very soon. So I hope this is clear and what relations are trying to capture. Fine, we'll see more examples as we go on. So let us briefly discuss a very fundamental notion in mathematics, which is that of graphs. In high school, when we say a graph, what we mean is a function and then we plot that function, that one data on x-axis, the other data on y-axis, etc. But when we say graphs in this context, the kind of graphs that we are discussing, they are not at all about plotting any function or anything. It's just an unfortunate clash of terminology. So when we say graphs, what we mean is you have a bunch of points. Intuitively, this is the, we'll define it formally, but the intuitive notion is you have a bunch of points, and then some of the points are joined by edges. Some may not be, but some may be. So here you have 3 points and then 2 edges. Here you have how many? 6 points and then 3 edges. And you may have no edges at all. That's also a graph. Right? And then here you have 4 points and then all the possible edges are there. So that's also a graph. A graph is a very general object. Alright, so that's a graph. But graph has nothing to do with how you draw them. Graph is a very abstract mathematical object. We think of graphs as these pictures, but the formal definition has nothing to do with how you draw the graphs. So for instance, you do not necessarily have to have straight edges. The straightness of this edge is merely for aesthetic reasons. One can draw it this way also, that's also fine, and they can cross, and so this is not, these are not to be thought of as geometric objects. So what is the formal definition? Here is one way to express the formal definition of a graph. There are other ways, but we'll express them in terms of relations. So a graph, or a simple graph, what we are really defining is a simple graph. A simple graph is a set V along with, or rather is a pair V comma R, where V is a set and R is an irreflexive and symmetric relation. On V. So pictorially, what does irreflexivity correspond to? It means that you don't have loops, right? So please make sure that you get that point, that when you jot down. Okay, so first let us see, how do you develop this picture out of this data? So what you do is you have some set of vertices. So yeah, so these are called vertices. Once you have a graph, these are called vertices, right? So what you do is you're given some data of this sort, where R is an irreflexive and symmetric relation on a set. So what you do is you just plot, or rather just draw all these points that are there in V. So V1, V2, V3, V4, let's say there are 5 points in V, and then whenever there is V2, V3 in R, you just draw this edge. And since it is a symmetric relation, you don't need to put an arrow or anything. It's just an edge, right? So this is how you develop this picture. And irreflexivity simply means that you do not have a loop. A vertex is not related to itself, so you don't draw the loop. In general, you can allow for loops. Those are then not simple graphs. When we say simple graphs, we mean no loops. So right, so that's a definition, an example of a relation. And although it's not important, but let me leave you with an exercise. So given a graph, let V comma R be a graph. Define for a vertex the degree of the vertex as those vertices, or rather the cardinality of those vertices which have the property that V comma X is in the relation. So what happens in this figure? Suppose this is your vertex V, then what are the points in the vertex set such that this happens? These are this point and that point. These 2 points have that property because we have an edge here and an edge here. So what is the degree of this guy? The degree of this guy is 2. The degree of this guy is 1. The degree of this guy is 1. The degree of this guy is 2. This is 1. This is 1. 1, 1, and 2. This is 3, 3, 3, 3. So that's the degree. And okay, so I'll give you a simpler version of the exercise I had in mind. So it's the following. Show that if V is finite. In the definition of a graph, V does not have to be finite. So I mean, generally when we say graphs, we mean finite graphs, but it's not necessary that one deals with only finite graphs. So show that if V is finite, then this quantity, the summation of all the degrees, is even. So what happens here? Here you have a 2 and a 1 and a 1. And what happens if you add all these numbers? You get a 4. 4 is an even number. This is a 2, this is a 2, this is a 1, this is a 1, 1 and 1. So the total is 2 plus 2, 4, 4 plus 4, 8. So this 8 is an even number. And here 3, 3, 3, 3. You are adding 3, 4 times. So of course you're going to get an even number. So that's a 12. 12 is even. So this is what I would like you to try, and one possible approach is use the well ordering principle. But for using well ordering principle, you need to have, somehow map the problem to natural numbers. So well ordering principle on the number of vertices. Figure this out. It's an instructive exercise. Okay. Another very important class of objects in mathematics are posets, or partially ordered sets, as fundamental as graphs. So here is how we define them. So let P be a set a partial order on P is a reflexive antisymmetric and transitive relation, and I haven't defined transitive. So let me define what I mean by a transitive relation. Let me define it here. A relation R on X is called transitive if X R Y, Y R Z imply that X R Z. So what this means is that whenever we see that X is related to Y and Y is related to Z, then X is related to Z. It's transitive, right? It's kind of, if you sort of, so to say, if you can go from X to Y and you can go from Y to Z, then you can go from X to Z. Right? So that's the kind of, so this is also very good terminology is all I'm trying to say. So partial order is a reflexive antisymmetric and transitive relation. A partially ordered set is a pair P comma a symbol where this symbol is a partial order. On P. So this may be confusing because this symbol is used to denote the order relations on things like integers and natural numbers, etc. In a general partially ordered set, we continue to use the same symbol because it is really in the same capacity that we use it. If you feel that this is confusing, you can put an R here and that's completely fine, but I would encourage you to develop this skill of being flexible with the notations. So do not confuse this symbol with the ordering of natural numbers. This is a generalized notion of ordering. A partial order is a more general notion of the kind of ordering that we are used to. And it is a good idea to keep using the same symbol. So again, this definition is somewhat abstract looking, so we will reinforce our understanding by examples. Here is a very good example of a partially ordered set. So first I need to define what is a power set. So if so let x, should I use x? Yeah, let's use x. So let x be any set. Then the power set of x is defined as the set of all subsets of x, including the empty set. We denote the power set of x by p of x. We denote the power set of x as, we make a script p and then an x. So we have defined power set. And let us quickly see an example. Suppose x were equal to a, b, c, just a 3-element set, then the power set of x would have the empty set, then all the singletons that one can form using elements of x, then all the doubletons, and then finally the entire thing itself. So this has 8 elements. Exercise. Let x be a n element set. So if the cardinality of x is n, then show that the power set of x has cardinality 2 to the n. And if you like, you can use the well ordering principle. Well ordering on what? On the cardinality this time. I highly encourage you to not skip any exercises. Okay. So that's the definition of the power set, and now we'll give a poset structure, a partial order on the power set of any set. So this is also called a poset. A partially ordered set is called a poset. So we take the P, we take the O, and we take the set. Okay, so let X be any set. And P be the power set of X. Define, or for two elements A and B in P, write A less than B if A is contained in B. So A and B are in P, meaning A and B are subsets of X. So we can talk about whether or not one is contained in the other. And basically what this says is that this pair is in the relation that we are defining if the first guy is contained in the other guy. So clearly this is reflexive because A is always contained in A. So we check that. 1, this is reflexive. Nothing to check here because A is contained in A for all A in not just the power set but for every set in the universe. Second thing is antisymmetric. So what does that mean? It means that whenever we have distinct elements A and B with this holding, we cannot have the other way around. So what you need to check is that if A is contained in B but A is not equal to B, then B is not contained in A. This is what you need to do. I just spelled out the meaning of this. And the third thing is transitivity. Which means what? If A is contained in B and B is contained in C, then A is contained in C. Okay? So just check all these things. Hardly anything to check though. Basically you need to verify that all these three things are holding. Okay? And now finally the pair let me use this symbol, is a partially ordered set. Right? So that's a very, very nice example of a partially ordered set. Anyway, so that's that. And now let us discuss if there's anything about relations that you should know about equivalence relations. And I don't know if we will be using the notion of a graph or a poset in the entirety of this lecture series, but we'll definitely be using the concept of equivalence relations here and in any other lecture series that I'll be making. Okay, so what is an equivalence relation? A relation, we usually write sim. I don't know how you read this, maybe a tilde. So a relation tilde on a set X is called an equivalence relation if tilde is reflexive, symmetric, and transitive. And of course the importance of this may not be clear just by the definition. So let us look at least one example. So define a relation on natural numbers. So define a relation tilde on natural numbers as by writing A tilde B if, okay, before I get there I should have said, so fix some positive integer, fix some natural number n, and now once you fixed that, we are defining a relation. So after fixing that number, define a relation tilde on natural numbers by writing A tilde B if A and B, okay, if n divides A minus B. Or let us define this on integers rather, it doesn't matter. on the set of integers. Could have defined it on natural numbers also, but let's define it on integers. If n divides the difference of the two. So, okay. So tilde is reflexive. What does this mean? This means that n divides a minus a, which is nothing but 0 for all a, for all integers. That's what this means. But this is true, of course, because every natural number divides 0. 0 is divisible by every natural number. Tilde is symmetric. Which means that if n divides a minus b, then n divides b minus a. And this should also be very, very clear. And lastly, tilde is transitive. If n divides a minus b and n divides b minus c, then n divides a minus c. That's what it means, and this is very easy to see because if n divides these two things, it will also divide the sum of these two things. But the sum of these two things is precisely that. Right, so this is an equivalence relation on the set of integers. Okay, so now here is one very nice fact. So I need a definition. Let X be any set a collection x1, or it could be just anything like, a collection, maybe I'll write script p of subsets of x is said to be a partition of x if some conditions are satisfied. So basically what we are doing is, this is not the power set, this is just some collection of subsets of x. We say that this collection of subsets of x is a partition if, first of all, each element of x must be in some element of p. So for all x in x, there is, okay, let me use the formal symbol, there exists. This is the symbol for there exists. There exists some element of this script p such that x in p. So every element of x lies in some element of script p. This is same as saying that the union of all the elements in script p is x. So make sure that you understand this equivalence, this statement and that statement. This looks like a longish statement, but it is saying something very, very simple. Just draw a picture. So you have this x, and then you have these elements of this p, and every element of X is in some member of P. So basically, this is the covering condition, that these things cover X. That's what the first condition is saying. The second is that no two things in P overlap. So if A and B in P and A is different from B, then the intersection is empty. So the elements of P cover X and the elements of P do not overlap. So pictorially, if this is X, the elements of P basically look like this. You've broken X into pieces such that the pieces do not intermingle. Right, so that's what a partition is, and that's a very nicely chosen terminology. This is what a partition looks like anyway. That's a partition. And now another definition. So let tilde be an equivalence relation on a set X. Let X be some arbitrary element in X. Then the equivalence class of X, of little x, what am I writing? Of X is defined as the set of all elements of X, all elements Y in X, such that X is related to them via tilde. So this is in words. In symbols, the equivalence class of X is written can be expressed as follows. So those elements in X such that X is related to Y, and the notation for it is we write X and then we put a bracket around it. And this can be ambiguous because if you have two different equivalence relation on the same set, then this is ambiguous. Which relation are we using to take this equivalence class? If such a thing happens, then we put a tilde at the bottom also, just to emphasize which relation are we using. So for instance, one could be using a tilde and this some other symbol at the same time. So you just put that there to emphasize which one you're using. So when there is no confusion, we don't do that. We just put this bracket and understand that we're talking about the equivalence class. So we'll prove some properties about the equivalence class and connect them to partitions of the set X. Sorry, this is tilted. Right. So here is the lemma. Two distinct equivalence classes do not intersect. So here is how we'll do it. So let A and B be equivalence classes of X and Y respectively. So in other words, A is the equivalence class of X and B is the equivalence class of Y. Okay, and suppose A intersection B is non-empty. So assume A intersection B is non-empty. We will show that A equals B. And therefore, what we will be showing is that whenever two equivalence classes intersect, they are actually the same equivalence class. So two distinct equivalence classes will not be intersecting. This will prove the lemma. Okay, so let Z be in A intersection B. Since A intersection B is non-empty, we can pick an element in the intersection. So this is your A, this is B, let's say this is X, this is Z, and this is Y. So since Z is in the equivalence class of X, we have X is related to Z by definition of equivalence class. And since Y is in the equivalence class of, since Z is in the equivalence class of Y, we also have this, but by symmetry we have Z tilde Y also. And now by transitivity, if you apply transitivity here, what you'll see is that X is related to Y, right? So therefore, if Y prime is in the equivalence class of Y, we have Y tilde Y prime, which implies again by transitivity X tilde Y prime. So because we have this and we have that, apply transitivity, you will have X tilde Y prime. What does that mean? Which in turn means that Y prime is in A. Because what is A? A is the equivalence class of X. So whenever you have X tilde anything, that anything is in A by definition of the equivalence class. So what this shows is that B is contained in A. We picked an arbitrary element in B, and then we ended up showing that it lies in A. So B is contained in A, and similarly, by similar reasoning, by the same reasoning, by a similar argument, we have A is contained in B, and thus A equals B. Because if B is contained in A and A is contained in B, then those two things must be equal. So that's it. That's the proof. So two distinct equivalence classes do not intersect. And now finally, if you want to call it a theorem, it's a theorem that the set of equivalence classes of any equivalence relation partition any equivalence relation next partition the set partition X. I will write X. So if you have an equivalence relation of X on X, then you collect all the equivalence classes and they will partition the base space X. The reason is very simple. We've already shown that two distinct equivalence classes do not intersect, and clearly every element is in its own equivalence class by reflexivity. So the covering condition is trivially satisfied, the first condition. So that's it. I mean, I'll leave you to fill the details if you are feeling uncomfortable. So we have given full details for this theorem. And now here is a final point. So given an equivalence relation, or before that, let us pose an exercise. What are the equivalence classes under this relation that we discussed? Where is the relation? This one. So this is a relation. So let me call it the divisor relation. I don't know what is the formal name for it, but let me call it the divisibility relation for the purpose of this lecture. With respect to n. So what are the equivalence classes? Of the divisibility relation? With respect to a given integer n. And of course this is not at all hard, but one should maybe try to put n equals 2 and see what happens, and then equals 3, then see what happens, and from there you can make a guess. Okay, and now let me do the rest of the things in a fresh page. So given an equivalence relation, on a set X, we denote the set of all the equivalence classes generated by tilde, or whatever you want to, howsoever you want to phrase it, a set of all the equivalence classes as X, then we put a slash and then a tilde, and this is read as X mod tilde. So X mod tilde, whatever relation that might be. So that's a notation. And we just saw that this is a partition of X. So again, let pi sub X denote the set of all partitions of X. So then we have, so this is just another notation, and let script E sub X be the set of all equivalence relations on X. So what we have is a map. We have a map from Ex to pi x. What does this map do? This map takes an equivalence relation and gives us the set of all the equivalence classes. This is the legitimate map, is all that we just did. Whenever you are given an equivalence relation of X and you collect all the equivalence classes, that forms a partition of X. That's all that we proved so far. We want to give a map in the reverse direction such that that reverse map is the inverse of this. So that's very easy. Basically, given a partition pi of x, we define a relation tilde sub pi. It looks very weird, but what can you do? Tilde sub pi on x as follows. So what is tilde sub pi? It's those pairs x comma y and x cross x such that x and y are in the common part. So there exists a set P in pi such that x and y both belong to P. So what are we doing? We have been given a partition. We have this. Okay, let me use a different color. This is our x. We have been given a partition. I can only draw a finite partition. And what are we doing? Whenever we pick two elements from x, let's say we pick these two elements and we notice that, well, they are in a single part, then we say that they are related. And if we pick two elements and they happen to be in different parts, then we say that they are not related. We do not put them in this box. Right, so that's what this is saying. Right? And I leave you to check that this is an equivalence relation. So check that is an equivalence relation. Fine, so we get a map in the reverse direction. Call this G. What does it do? It takes little pi and gives us tilde sub pi. Right, and here is an exercise that I want you to do. So if you go this way and then this way, then what I want you to show is that this is identity. Show that the pink map is identity. Meaning what? Meaning it takes an equivalence relation and gives you the same thing back. And also show the other way around. So if you start at pi x, you go via G, and then you go via F, then this time let me use a different color. So this time you show that this is identity on pi x. So if you start with a partition, you generate the corresponding equivalence relation and then generate the partition from that, you'll get the same thing back. So the point of this is that the set of all the partitions on x and the set of all the equivalence relations on x are basically the same objects, dressed somewhat differently. And what identifies what is the dictionary between these two different languages, these are the dictionaries. If you are comfortable in this world, you pass to this world via this dictionary, And if you're comfortable with this word, then you pass to this word via this dictionary. And these two dictionaries, they respect each other in this, formalized in this exercise. And one should be comfortable with both the words. It's not like, no, I'm an equivalence relation person, or I am a partitions person. No, there's no such thing. You are both. Okay. So that's it. Please do all the exercises. Don't skip anything. And this is all that I wanted to say in this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.